So let me remind you some stuff. From 17b, solved some differential equations. And this is probably like one of the easiest ones we solve. Dx dt equal to a times x. We can definitely separate the variables. Bring the x's to the left, the t's to the right. So I would rewrite this as 1 over x dx equal to a dt. And then we would, of course, integrate both sides. The integral of 1 over x is the natural log. Well, so I'm going to ignore the absolute value because it doesn't end up being a big deal. It's the natural log of x. Yes, I know it's really the natural log of the absolute value of x, but it doesn't end up mattering. And that's going to equal the antiderivative of a, which is a times t plus a constant. Yes, there could be a constant on both sides, but we just bring it over to the right-hand side, so it'd be more constant. And then solving for x, we have the e to the natural log of x equals e to the at plus c. So that's going to be x as a function of time equal to e to the at times e to the c. We're going to call this a new constant, often just big C. And then our solution is going to be x of t is a constant times e to the at. And I want to point out, this really is a solution, right? If you take the derivative, dx dt, the derivative of constant times the function is the constant times the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And what's the derivative of at? Everybody. What's the derivative of 7x? Right. So what's the derivative of a constant times the variable? Just the constant. So what's the derivative of at? Right, it's a. But look, that's exactly a times x. So the derivative of this is really a times x, just like we started out with. So I just want to make it expressly clear that when you differentiate, when you're solving dx dt equal to a times x, your solution ends up being ce to the at. That's our solution right there. X is a function of time. C times e to the at. It's an exponential function. And a couple other things. We know that this here, this differential equation, dx dt equal to a times x, describes x growing exponentially as a function of time. Well, actually, I should be a little bit more specific here. It could be growing or it could be decaying. We know that if that constant a is greater than 0, so if that constant there is greater than 0, then as time increases, this whole value is going to increase. So if a is greater than 0, then we have growth. And if a is less than 0, then we have decay. Awesome, thanks. Okay, so hold on to that thought for a few minutes. We're gonna definitely circle back around to that, but we're gonna talk about the matrices again, because the matrices are definitely where we're going. I'll come back to you, you're important. So let's look at this example. Let's find the eigenvalues and eigenvectors. I know it's been a while. Of a equal to -1, sorry, a -1 to -3. This is definitely a process you're going to want to be able to get good at because you're going to do it a lot over the next 3 weeks. So to find the eigenvalues. And typically, you almost always, I guess this isn't entirely true, but most of the time, you need the eigenvalues to find the eigenvectors. So you almost always start by finding the eigenvalues and then finding the eigenvectors. You can kind of go the other way if you know something already, but that's not what we usually do. So we're going to solve the determinant of a minus lambda I equal to 0. So we're going to do the determinant of -1, 2, -3, 4, minus lambda times 1, 0, 0, 1. You don't need to write this step, right? I'm writing an extra step here. You should really jump straight to saying, okay, the determinant of -1 minus lambda, 2, -3, and 4 minus lambda. The determinant of that is equal to 0. So you always just subtract a lambda in every diagonal element. Oh, sorry, I forgot the video. I always forget the video down here. Not always, but it's a lot of the time. Sorry, people. I know you really want to see me, so you can see my cool Nightmare Before Christmas mask. Yeah, it's great. I might pick it up. I really like it. All right, so solving this, it's going to be -1 minus lambda times 4 minus lambda minus 2 times -3 equal to 0. Or more generally, right, product of the diagonals minus product of the off diagonals. And then multiplying this out, let's see, we have negative lambda times negative lambda is lambda squared. And a minus 4 lambda plus a lambda is going to be a minus 3 lambda. And then I have a minus 4 plus 6 is plus 2. And I should point out, because I do think it's worth pointing out, you could jump to here without doing this work. If you really want to be kind of slick about it, I'm just going to show you a couple things. What's the, and you guys might have forgotten, the trace of a matrix is just the sum of the diagonal elements, which is in this case, -1 plus 4. And the determinant of the matrix is, you have to use the capital delta, and it's -1 times 4 minus 2 times -3, which is indeed equal to positive 2. I want to show you that it's not a coincidence that that number is 3 and that number is -3, and that that number is 2 and that number is 2. It is always the case that when you find this characteristic polynomial, which is what this thing is called, it's always going to be lambda squared minus the trace of the matrix times lambda plus the determinant of the matrix equal to 0. You don't have to do it this way. You can totally go through these steps, but this is an alternative way of getting there that might be a little bit faster. Either way is fine. Really, either way is fine. I just want you to have options. So then solving this, we have lambda minus 2 times lambda minus 1 equal to 0. So our eigenvalues are, I'm going to say lambda 1 is 1 and lambda 2 is 2. It would be silly to call them the other way around, right? Like it would be really, really dumb to say lambda 2 is 1 and lambda 1 is 2. Normally, I make lambda 1 the bigger one and lambda 2 the smaller one, but I think this is a good exception to that convention. Great. We've got the eigenvalues. So now we're going to find the eigenvectors. Just want to make sure I'm not saying this. I want to circle this here. All right. So to find the eigenvectors, we're going to solve, and again, there's kind of two ways of doing this as well. You can either solve A times the vector equal to lambda times the vector. That's kind of my preferred way of doing it. Or you can solve A minus lambda I times the vector equal to the 0 vector. Either way is good, either way. Sometimes there's advantages to doing it this way, sometimes there's advantages to doing it this way. I feel like in a different class we'd want to do it this way more, but there was one class taught by not this guy. So yeah, we'll do it both ways just so you can see both. Also, before I forget to mention it, please do fill out the attendance form when you have a second. Yeah, so let's do lambda1 equal to 1. So we're trying to solve a times the vector equal to 1 times the vector. The vector that we don't know, right? We're trying to find the vector v. Since we don't know what it is, we're just going to use variables in place of it. So I'm going to write A, which is the matrix, -1, 2, -3, 4, times the unknown vector v, which we usually use x and y for, and there's a good reason for this, equals 1 times xy. And the nice thing about doing it this way is you really only have to use one of the equations. So what does this really mean? This really means -x plus 2y equals x and -3x plus 4y equals y. Right, that's what this multiplication actually means. I only need one of those to figure out what x and y are. Well, in fact, I should actually point out. No, actually, I should do that. So I'm going to use the first row because I always use the first row unless it doesn't work. Let's isolate y. So I'm going to get 2y equal to 2x, y equals x. Pick any number for x you want except for 0. 1 is the standard choice. You could pick 6, you could pick a billion. We're going to pick 1. So the eigenvector here, which is xy, is 1, 1. And I should also point out this line, which is why it's nice to solve for y in terms of x. This line y equals x is the eigenline. Meaning if you graph that line, any vector that terminated on it would be an eigenvector. We're going to talk more about eigenlines a little bit later, but the eigenline is really just the line that the vector lives on. So if you plotted the vector 1, 1, you go over 1, up 1 from the origin, and the line y equals x completely encapsulates that. In fact, why don't I just draw it? There's the vector 1, 1. And here's the eigenline y equals x. And hopefully you can see that, right? If we stopped at any point on that line, it would also be an eigenvector. So 2, 2, 3, 3, -2, -2, etc. For the second eigenvector, I'm going to find the eigenvector the other way, meaning instead of solving a times v equals 2 times v, I'm going to solve a minus 2 times v equals the 0 vector. Which again, I'm going to write as matrices. So A is still the same matrix. It's -1, 2, -3, 4. And I'm subtracting 2 times the unknown vector v. Right? We're pretending like, well, we're not pretending, we don't know what v is. Okay, so I really should put this together. And I feel like I've made a small mistake here. Oh, I did make a small mistake. I forgot something important. I made a big mistake, actually, not just a small mistake. Look over, oh, sorry, you can't see it. Maybe that's why you guys can catch it. I did a times a minus lambda v when I should have done a minus lambda I times v. Now, how did I know I made a mistake? Well, look at this. That's a matrix that's 2 by 2. That's a matrix that's 2 by 1. I can't subtract those together. That's a big problem. We really should have been doing this. A minus 2 times the identity matrix times v is equal to 0. So we really should have And again, I just want to do this as one thing, right? So A is -1, 2, -3, 4. And I'm subtracting 2 in the diagonals. So it should be -1 minus 2, 2, -3, and 4 minus 2. Times V, which I don't know, equal to the 0 matrix. So then I'm going to simplify a little bit. That's going to be, let's see, -3, 2, -3, 2. It's pretty common that when you do it this way, both rows look the same, or that there are at least multiples of each other, not exactly the same. So this translates to -3 times x plus 2 times y equals 0. Solving for y, I get 2y equals 3x, which is where I usually like to leave things. This doesn't feel very bright. But you can also solve for y and say y equals 3/2 x. The nice thing about writing it is 2y equal to 3x. It's really, really obvious what the easiest choice, or I should say, the quote unquote nicest choice for your vector is. An easy way to solve 2y equal to 3x is to let x be 2 and y be 3. Or to let each variable be the other one's coefficient. So 2 is the coefficient of y, let that be x. 3 is the coefficient of x, let that be y. Then you have 6 equal to 6. You've got a solution. And we can say that the vector is, well, I just said x should be 2 and y should be 3. That's the choice that's going to have kind of the smallest integer values, right? You could pick any multiple of that, 4, 6, 1, 3/2, not 0, 0, right? 0, 0 is never a good choice for an eigenvector, but any other multiple is perfectly fine. And then a couple labeling things. I should really call this V1. I should really call this V2. Right? We'd like to have different names for our eigenvectors. If this is lambda1 equal to 1, I should call this V1. That's the one associated to it, and similarly here. And yeah. All right. So those are the eigenvectors for this matrix. Eigenvalues are 1 and 2. Eigenvectors are 1, 1, and 2, 3. Once again, we could have made different choices, but usually people are going to choose the eigenvector that those really itches. I'm sorry, like just like terrible. Sorry. We're going to choose eigenvectors that have nice integers and are as small as possible. So these are kind of the typical choices for eigenvectors in this particular problem. All right, so now let's actually get to the point of what we're doing in section 10. We're going to use both of this and what we just did before. Provided I can stop itching my nose because it really itches. All right. So let's let x of t be the population of a predator. Let's say wolves. And let's say y of t is the population of a prey. Say deer. So we're going to say that dx dt is the growth rate of the wolves. Dy dt is the growth rate of the deer. And just to be clear, right, if dx dt is negative, it means the wolves are decreasing in their population size. If dy dt is negative, it means that the deer population is decreasing in size. So positive growth rate means you're increasing, negative means you're decreasing. Also, for those on Zoom, right, feel free to, if you got questions, comments, whatever, let me know. So we would kind of expect these populations to be dependent on each other. So we kind of have to study them together, right? It doesn't make sense to just look at the rate of growth, the growth rate of wolves, without thinking about how the deer population is doing. And vice versa. It doesn't make sense to just think about how the deer are doing without considering what the wolves are doing to them. So we're going to consider them together. We have this system of differential equations. Here it is. dx dt is going to be negative x plus 2y, and dy dt is going to be negative 3x plus 4y. And that's our system. And we also have some initial conditions. X at time 0 is equal to 2. So we're saying at time 0 there are 2 wolves, and y at time 0 is 4. At time 0 there are 4 deer. Not a lot, but okay, it's a made-up problem. Gosh, I'm sorry, my nose is just really, really itchy. Okay. So let's think about what this means for a second. If there were no prey, so if there were no prey, that is, if y were equal to 0, then we would have dx dt equal to what? Well, what are we left with? Just negative x. But we know what that means, right? This is exactly like the thing we did in the beginning, right? Where dx dt equals ax. It's just here dx dt is equal to negative 1 times x, which would mean we'd have exponential decay because our a constant is negative. So this would mean that the wolf population would exponentially decay. Which makes sense, right? If there's no prey, there's no food. If there's no food, you can't make more. You're going to start dying off. And similarly, now, okay, obviously there's lots of factors we're not taking into account biologically, right? There's a lot of things you don't consider when you try and make your model simple. We're pretending like the deer can just eat food and be fine if there's no wolves. So if there were no predators, that is, if x were equal to 0, then dy dt would be 0 plus 4y, which would mean exponential growth for the deer. Which again, at least with our model, makes sense. All right. So we would like a way of describing kind of how many predator and prey there are at any particular time t, right? Just like we can solve this differential equation with x equals ce to the at, we really like to be able to solve this system of linear differential equations in a similar fashion. And the answer is we can. The answer looks a lot like it did before. So here is what we are really solving. We can rewrite this. In fact, let me look back at it. So yeah. We can rewrite dx dt equal to negative x plus 2y, dy dt equal to negative 3x plus 4y as the matrix, the matrix equations dx dt, dy dt equal to the matrix negative 1, 2, negative 3, 4 times the vector xy. Exactly the same system of equations, just written a different way. And that happens to be the matrix we were dealing with earlier on purpose. And here's the idea. If dx dt equal to a times x has the solution x of t equal to c e to the at, then what we have here is the derivative of the vector. So we often call this the vector dx dt equal to the matrix times the vector. Oh, sorry, this is not the vector x. This is the vector that's the derivative of x. This is the vector x. We're trying to solve that. we're trying to solve the derivative of this vector is equal to the matrix times this vector. It looks very much the same. And that equation, pretty similar looking. And so it would be nice, it's not exactly true, but it would be nice to say that this has a solution like, although not actually, x bar equal to c e to the at. The problem is, it's perfectly fine to have a here. A is just a constant. But here, A is a matrix. And although in higher math classes, people actually do talk about defining e to the power of a matrix, that's not what we're doing in this class. It's not what we need to do in this class. There's definitely a way of actually getting this. So since we can't do that, we're going to use the eigenvalues instead. So instead of, we don't want x equal to ce to the at, what we're going to do instead is say that x as a function of t, right? You can call this x of t if you want. It's going to equal c1e to the lambda 1t times the first eigenvector plus c2e to the lambda 2t times the second eigenvector. And that is definitely an equation you're going to want to memorize. It's going to come up a lot. You might feel like it looks a little long. It's not that bad. You're definitely all going to memorize it without issue because you're going to see it a bajillion times. So this is called the general solution for a linear system of differential equations. Any questions before we do more with this? Other than why is it, we're going to see why it's a solution in just a second. So let's go back and look at the system we were dealing with, which was this here. We already know the eigenvalues and the eigenvectors for this matrix. So we're just going to write it out. So we're looking at solving, or I should say, the general solution to dx dt, dy dt equal to this matrix A times, you can either say this is x or x of t and y or y of t. Either way. Is x of t as a vector, which is regular x, regular y. It's going to equal all this. We don't know what C1 and C2 are yet. We do know what lambda 1, V1, and lambda 2, and V2 are. So I'll remind you, lambda 1 was 1, and V1 was the vector 1, 1. Lambda 2 was 2, and V2 was the vector. I don't remember actually what the V2 vector was. Let me go back and look. I think it was 2, 3, or was it 3, 2? It was 2, 3. There is our general solution. And now we're going to use the initial conditions to find our constants. So initial condition is that x of 0 was 2, y of 0 was 4. So when I plug in t equal to 0, I get x equal to 2 and y equal to 4. So you get c1 e to the 0 times 1, 1 plus C2 e to the 0 times 2, 3. Simplifying this, I have 2, 4 equal to C1 times 1, 1 plus C2 times 2, 3. There's a number of ways you can solve something like this. It's a system of 2 equations and 2 unknowns. You could say 2 equals C1 plus 2C2, and 4 equals C1 plus 3C2. And then probably the easiest thing to do in this particular situation is just subtract the equations from each other. So this equation minus that equation gives you 2 minus 4, C1 minus C1, 2C2 minus 3C2, so that C2 has to equal positive 2. And then C1 has to equal, well, if that's 2, then C1 has to equal also negative 2. Or sorry, not also, C1 equals negative 2. Great, so here is our final particular solution. Particular solution to dx dt dy dt equal to -1 to -3, 4 times x of t, y of t is x of t, y of t equals all of this with the particular values for C1 and C2. So it's going to be -2 e to the t times 1, 1 plus 2 e to the 2t times 2, 3. And now here's what I want to say about this. Most of the time people leave it like this. I would leave it like this for sure. Sometimes it feels convenient to put it all together, meaning I actually want to write this as one vector. So check this out for just a second. This isn't a huge deal, but we could rewrite it as x of t, y of t equals -2 e to the t times 1 plus 2 e to the 2t times 2. So that's 4 e to the 2t. That's what x of t is equal to. And y of t is going to be -2 e to the t times 1 plus 2 e to the 2t times 3. So there's the solution. There's a vector kind of written nicely. And then you could even say we just have x of t is -2 e to the t plus 4 e to the 2t. Y of t is -2 e to the t plus 6 e to the 2t. Okay, kind of a lot. But this is the process for solving a linear system of differential equations like this. You find the eigenvalues, you find the eigenvectors. You write this general equation. Sorry, this general solution. C1 e to the lambda 1t times v1 plus C2 e to the lambda 2t times v2. Maybe you solve for C1 and C2 if you're asked to. And then there's your final solution, like that. I got this in the right order. I have one more thing to say about this, and then I think you guys might have some questions. If you have, or if you don't, that's also okay. But let me say one more thing. This is actually a solution, right? So I just want to point out, this is, in fact, a solution to the original question. Dx dt equal to -x plus 2y, and dy dt equal to -3x plus 4y. Right, we're not just like making things up. This actually solves this. We can show it. So if I look at this really quickly, it's kind of it's not that bad. Let's find both sides of this equation. So dx dt, just taking the derivative of x, is, well, nicely, the derivative e to the t is easy. It's just e to the t. So the derivative of this is going to be -2 e to the t plus 4 e to the 2t times what? What do I need to multiply by when I take the derivative there? Yeah, thanks. Right, derivative e to the stuff is e to the stuff, then to the stuff. And so that's negative 2 e to the t plus 8 e to the 2t. Let's compare that to negative x plus 2y. Well, negative x is the negative of all of this. So it's negative 2 e to the t plus 4 e to the 2t plus 2 times y, which is all that. So let's see. I'm going to get, I'm going to get worried is what I'm going to get because this looks wrong. Oh no, it's not wrong. I'm just making mental errors in my head. So here we've got a plus 2 e to the t. Here we've got a minus 4 e to the t, and they add up to give me a negative 2 e to the t. Good, we're on track so far. And then here I've got a minus 4 e to the 2t plus 12 e to the 2t, and negative 4 plus 12 is 8. Those are the same. Check. And although I don't want to do it, I think it would be worth all of your time to actually check that both dy dt and what do I got here? Sorry, negative 3x plus 4y are actually the same. By taking the derivative of y, which is this, and then plugging in x here and y here, and seeing that you actually get the same thing. But we don't really do that much of the time. We're not usually checking to see that they're actually the same. We're just like, yeah, this process works. We don't have to check because we know the process works. So let me pause for a minute, take a drink, and ask you, do you have questions? Zoom folks, questions? Oh yeah, please.
When we plugged in the initial condition into the general solution, could you repeat why we got e to the 0?
Sure, yeah, good, yeah. We got e to the 0 because the initial condition, at least for this problem, was that time was equal to 0. Right? We're saying at t equal to 0, x equals 2, and at t equal to 0, y equals 4. And almost without fail, when you're in these sorts of problems, you are definitely going to have initial conditions at t equal to 0. Like no one's telling you how much stuff you have at time 1 or 2 because it just isn't particularly nice to solve. Because then you're going to get e to the something that isn't just 0, and that's going to be kind of gross. Yeah, so a couple things. One, just a warning. A lot of the time, these are nice. A lot of times you have nice values, you have nice eigenvalues, nice eigenvectors, everything's great. But some of the time, we're going to have imaginary number eigenvalues. And we're going to have, if we're asked to find them, which a lot of the time we're not, but if we are, if you have imaginary eigenvalues, you also have eigenvectors that have imaginary numbers in them. And this is actually something we're going to consider because some of the solutions have imaginary things and they actually have meaning about what the solution system looks like, which is the last part we should talk about here. But before I go on, someone asked, what would the answer be? So the answer to this question, and let's remind ourselves what the question was, right? So we were answering the question, what's the solution to this system of equations with these initial conditions? And the answer, at least the way I would probably prefer to write the answer is, I would prefer to write it this way. But technically, any one of these three things I've written is correct. These are all the same answer, just written slightly differently. This first way of writing is probably the most typical way of writing it. Hopefully that helps out. Not quite done with this problem. A couple other things to talk about. So often, after we found this solution to our system of linear differential equations, we want to ask, well, what does this mean about the long-term behavior of this system? As time goes on, what's going to happen to the deer and the wolves? Well, that's a good question. So let's look at our general solution again. Or sorry, our particular solution. So what happens to both populations? As time goes on and on and on and on and on. I'm sorry, I kind of. Well, I've got something that's getting negatively infinitely large here, right? Because e to the infinity is infinity. So this is negative 2 times infinity times 1, 1. So both of these negatively infinitely large here. But over here, we're getting a positive infinity. So I guess the question is, of the two of these, which is bigger? E to the t or e to the 2t? E to the 2t is infinitely bigger than e to the t. It's a bigger infinity. I know my bigger there does not look like it's spelled very well. Sorry. It's a bigger infinity. So this infinity is bigger than that infinity, so we're adding more than we're subtracting. So both of these populations get infinitely large. Which, I mean, is obviously unrealistic, right? That doesn't make actual sense in the real world, but this is just math. So both x of t and y of t get infinitely large. A more typical question, why is there a negative in front of the negative 2e? Because when we solved for C1, right, when we back on the previous page, when we solved for the constants C1 and C2 by plugging in the initial conditions, when we did this work, we ended up getting that C1 had to be negative 2. Which makes sense, right? If we actually like plug in 2 for C2 and negative 2 for C1, 2 minus, sorry, I got this backwards, negative 2 for C1 and 2 for C2, negative 2 plus 4 is 2, and negative 2 plus 6 is 4. When you're doing the check. Here, the other page. Oh, here? Well, because it's coming from this equation here. So this was our original equation. And if you want to check the, or this, right, this one here, right? This was our original equation, negative x plus 2y. So if I'm actually checking it, right, I'm doing dx dt, I'm taking the derivative of that, which is, right, I'm just taking the derivative of that. And sorry, I lost my spot here. There's x, we're taking the derivative of that x to get dx dt. And then the negative x plus 2y, we're just taking the negative of that x plus the 2y. Right, it's just to check to see if, sorry, they're asking questions about like, why am I doing this? It's just to see if the solutions are right. This is totally an unnecessary step that you almost never actually have to do, but it's nice to actually see, oh yeah, this process worked, right? We're not just saying it works, it actually works. Sorry, you guys are like, what's he pointing to? If you can't see the thing I'm pointing to, please let me know. I was just talking about this right here, how we check this to see if there's actually a solution. So, yeah, yep, just to check. The other thing people kind of like to ask, oh my gosh, I get my slide back, is what's the ratio? Right, not the ration, the ratio of predator to prey as time goes on. That's a good question. Well, we could literally go back and look at our x and y. Kind of a pain. But here's x and here's y, and we could divide those by each other. But we actually don't need to do all that work. I'm going to show it to you anyway, just so you can see. But yeah, we don't really, no, I'm going to do it anyway. It's worthwhile. So Here's predator to prey is equal to x over y is equal to negative 2e to the 2t plus 4e to the 2, sorry, negative 2e to the t. There's so many things to keep track of. Plus 4e to the 2t over negative 2e to the t plus 6e to the 2t. So as time goes on, what matters the most? What gets the biggest, the fastest? E to the t or e to the 2t? E to the 2t. Now, what you could actually do is if you want to take the limit of this, you could actually divide everything by the thing that's getting the biggest, the fastest. Just like we've done before for like a polynomial over a polynomial, where we divide everything by like x cubed, if x cubed is the biggest power. I'm going to divide everything by e to the 2t and watch what happens. Negative 2, e to the t over e to the 2t is negative 2 over e to the t. So right, I'm dividing by 4e to the 2t over e to the 2t is just 4. Negative 2e to the t over e to the 2t is negative 2 over e to the t. And 6e to the 2t over e to the 2t is 6. And look what happens to these terms here. What happens to them? They go to 0. They cancel out. They don't matter because they weren't as big as the dominant term. They weren't the biggest thing. So what do we end up getting here? 4/6, or more importantly, 2/3, which is exactly, or as I might say, 2 predators to 3 prey, which is exactly always the ratio of the components of the vector with the larger eigenvalue. The larger positive eigenvalue. If they're both negative, this doesn't work. But if one of your eigenvalues is positive, or if at least one of them is positive, the ratio as time goes on of the top thing to the bottom thing is literally just the top eigenvector value to the bottom eigenvector value. So if this had been a different vector here, like if this had been 5, 6, our ratio would have been 5 predator to 6 prey. And that's always true. So if you do this sort of thing and you get at least one positive eigenvalue or 2 positive eigenvalues, whichever eigenvalue is larger, that eigenvector that goes with it is the one that tells you the ratio of the things. Kind of cool. So now we'd really like to see some stuff. And while you can totally like, I've got this picture of the direction field here. I'd like to show you guys how to do it. So let me show you. If you look in Desmos, sorry, not in Desmos. Desmos is not the tool you want. Although actually some people have made things in Desmos that kind of work all right. But really the tool you want is p-plane. So p-plane is fun. Downloading it's great if you have the time and desire to do that. But sometimes it's kind of a pain. But I just found a place to actually use it, which is kind of great. So if you go to the modules and you click on the right, you click on the use. I don't know why this one, oh, it's not published, James. You should publish that so you guys can actually use it. Great. Now you can go to the modules and actually find that thing. And you can type in your equations. So my first equation was, where was it? It was dx dt equal to negative x plus 2y. We've already got the dx dt, so it's going to be negative x plus, be careful with this. If you type 2y, it's not going to understand you. You have to write 2 times y. I learned that the hard way. And then our other equation was negative 3 times x plus 4 times y. All right. What does that mean? Well, what it means is that no matter where you start, so in fact, let's start at where we started. We started at initial condition of x being 2 wolves and y being 4 of the other thing, not sheep, deer. So I'm going to go over to the point, ooh, it's kind of hard to see, 2, 4, right out there. It's not going to be perfect. So that's, what does that tell me? It tells me that if you start at the origin and you travel in the direction of what's happening, you're eventually going to go through that 0.24, and you're going to keep going up that way, where the populations both get larger and larger and larger. Both x is getting larger in that direction and y is getting larger in that direction. And it's actually true no matter where you start. If I start there, well, actually, that's not entirely true. If I start there, it looks like one of them is getting very, very negatively large, which seems like a weird answer. But what we have here is instability. No matter where you start, you're shooting away from the origin. The origin is the only place of equilibrium. Right? If you have 0 wolves and 0 deer, they're not going to change, or I should say, their amounts are not going to change. And if you look at the equations we started with, sorry, you can't see what I'm writing. I realize as I start writing stuff down. If you look at the equations we started with, well, to be in equilibrium, you have to have no change. So the only way that this type of system of equations has equilibrium is if both of them are equal to 0. Right, this is going to be I just want to emphasize that again. Right? If we want to be in equilibrium, it means when the rate of change of deer and the rate of change of wolves is 0. That's what this says. The rate of change of wolves is 0. The rate of change of deer is 0. And the only solution to this system of equations, and this is very, very typical, the only solution is x equal to 0 and y equal to 0. One way to think about it is both of these are lines. Like I could solve this for y. Right, this line here, if I solve for y, would be the line y equals 1/2 x. And this line here would be the line y equals 3/4 x. Those lines both go through the origin. Those lines definitely have different slopes. So the origin is the only place where they cross each other. So 0, 0 is the only place where you actually have a solution to both of these at the same time. So for these linear systems of differential equations, the origin is the only point of equilibrium. That won't be true later on when we talk about nonlinear systems of differential equations. Sorry, I just want to make sure this isn't always true. This is just true for now. Yeah, and so the system is unstable as any initial condition other than 0, 0 takes us away from equilibrium. And again, I'll refer you to two things. One, I'll refer you back to the picture for just a moment, right? We are definitely emanating away from the origin here. Now, well, then we'll talk about what's a different example. And then two, I'll remind you that when we looked at our equations back here, out of order. Oh, my things are really out of order. That's not good. There we go. Okay, now we're back in them. All right, we saw that as time goes on, starting here, oh yeah, both the values x and y are getting larger and larger and larger. They're not getting close to any one particular value. That's also an indication of instability. Yeah.
Well, what would happen if it were approaching like a particular value?
So for these kinds of problems, the only particular value that we can approach is 0, 0. Meaning, at least when you're talking about animals, everything dies. That's really kind of the meaning. But let's actually, I think I have, I might not. Sorry, let me see here. I can make one up. So what if we have a situation where that's not the case? All right, other questions, just before we move on to another example, to make sure. Any other questions about this example? Yeah.
Are we only able to tell that this is an unstable system by graphing it?
No. Excellent question. The answer is definitively no. We do not need to graph it to know if it's unstable or stable. All we need to know is about the eigenvalues. The eigenvalues will tell us everything about the stability or instability of the equilibrium, which in these examples, we're always talking about the instability or stability of the origin, because that's the only equilibrium. But that's a really good, excellent question. And the answer is definitely not. All we need is the eigenvalues, which is kind of great news. Now, it's also nice to see the picture because it helps us actually see what's happening here. But no, we do not need them. I should also point out, when the origin is unstable like this, we say that we classify the origin as an unstable node, also known as a source, meaning everything is emanating from it outwardly. There are two types of ways things emanate outwardly. You can emanate kind of all just away, or you can emanate as a spiral. And I will certainly point out, even though this kind of, you might be like, James, that kind of looks spirally to me. It's not a spiral. A spiral definitely, you actually get like a full, like if this was a spiral, you would start somewhere and it would actually loop all the way around. Right? This doesn't do that. It kind of has a little bit of a turn to it, but it's definitely not a spiral. Really, the nicer way of knowing this is that you only get spirals if your eigenvalues are imaginary. So we definitely don't have a spiral here because our eigenvalues were real.
How does that show us that it's like stable or unstable?
So, well, you know what I didn't say, which was dumb, is that you look at the arrows. So here's what this phase plane really means. It means that if you plugged in the point, for example, if I plugged in the point, gosh, I feel bad. Like, let's see. So if I plugged in the point, say 1, 2, right? Is that 1, 2? Yeah. Well, in fact, let's look back at the equation for just a second. This is where things get a little dicey. Not dicey, just a little tedious. So here's our equation. dx dt equal to negative x plus 2y, dy dt equal to negative 3x plus 4y. And if we actually plug in the point, x is 1, y is 2, what do we get? Well, we get dx dt at 1, 2 is equal to negative 1 plus 2 times 2, which is 3. And dy dt evaluated at 1, 2 is, let's see, negative 3 plus 4 times 2, which is 5. Meaning that if you were to try and graph this this phase plane on your own, which you shouldn't. No one should be graphing phase planes by hand. It's never good. It's terrible. Like, I had to do it when I was a student. I hope no one makes you do it because it's not fun. But what it means is at the point 1, 2, the change in x is positive 3, meaning you're going 3 to the right, and the change in y is positive 5, meaning you're going 5 up. So we're going in the direction of the vector 3, 5. So we're going, now I don't want to draw that whole entire giant vector, right? That would take up way too much space on my phase plane. So instead of going over 3 and up 1, 2, 3, 4, 5, yeah. Instead of being like, I'm not going to draw that giant vector, I'm just going to draw the vector that's in that direction. So when we're at that point, we're going in that direction. And that pushes us over maybe to like this point here. And then when we're at that point, we plug it back into the equation, we do the whole calculation again, and you can see that it's awful. But we would get a new point, and if I just look back at my phase plane here, because honestly, that's what we should do, we can see, right, so from the point 1, 2, I'm moving kind of in this direction. Maybe I'm like right, maybe it gets me like right, I know it's not exact, right? But then from that point, you know, we could then plug it in again and see, like from there, we're still kind of moving in that same direction. So that's how we know it's unstable, because when we start somewhere, we keep moving away from the origin. Or our arrows are pointing in an away from the origin kind of direction. Yeah, good question. You had a question? Yeah, okay. We're definitely getting to your question. Any last questions about this example? Sorry, you guys can see my point. What time is it? Oh, it's okay. I better hurry up here. So let's say we had something like, I can just make an easy one like that. Yeah, smart. Let's say we wanted to find the solutions. Let's say we want to classify the solutions of this system. Dx dt equals negative 3x and no y, and dy dt equals 5x minus 2y. I'm not even going to, well, how much time? Sure. So with the initial conditions, x of 0 equals 2, y of 0 equals 10, which are probably terrible. How do I say all the words? There's a lot of words to say. So I want to point out that here's what the system looks like as a matrix. We have dx dt, dy dt equals our matrix times x, y. Oops, sorry. So our matrix here is negative 3, 0, 5, negative 2. And here's a great thing about this matrix. You already know the eigenvalues. If you have a matrix where the upper right corner or the lower left corner, or both, are 0, the eigenvalues are automatically the diagonal elements. I can still do the work, right? The determinant of a minus lambda I is the determinant of negative 3 minus lambda, 0, 5, negative 2 minus lambda. And that's going to be negative 3 minus lambda times negative 2 minus lambda minus 0 times 5 equal to 0. But I don't really need to do any more work here because 0 times 5 is just 0. I don't really want to multiply this out because I'm just creating more work for myself. This is just negative 3 minus lambda times negative 2 minus lambda equal to 0, which means either lambda equals negative 3 or lambda equals negative 2, which are exactly the diagonal elements from the beginning here. So if you luck out and you have either a 0 there or there, means that the eigenvalues are the diagonals. Or I should say the diagonal elements. Just to make sure everyone's super clear on what I mean by that. When I say the diagonal, I mean starting in the upper left corner and going to the lower right corner, the elements that are on that diagonal. On that, I can't say anything else, on that diagonal. And then we call the other ones the off diagonals. So our eigenvalues are negative. And I don't, yeah, fine. Sure. So the nice thing about when the eigenvalues are those diagonal elements is it's really easy to find the eigenvectors. So let's find the eigenvectors. For lambda equal to negative 3, and let's call that lambda 1. We're going to get that A times the eigenvector equals negative 3 times the eigenvector. But this is very easy to solve. The first row, well, actually, it's easy to solve if you know what you're doing. It's easy to be like, what the heck is going on if you don't? So the first row is negative 3x equals negative 3x, which means x should be what? 1's the right answer. What else is the right answer? Anything. X can be anything, which means we haven't really learned anything here. So this is actually a case where you really do need to look at the second equation. Most of the time, it's perfectly fine just to be like, let me check the first thing, get a condition, great. But here, we're going to look at the second equation and say that 5x minus 2y equals negative 3y. And then we have 5x equal to negative 2 plus, 2 plus negative 3 is negative y. So I would say that y equals negative 5x. So then I would say that x is 1 and y is negative 5. Let's check to be sure. If you plug in the eigenvector 1, negative 5 there, negative 3 times 1 gives you negative 3 times 1. Check. And 5 times 1 plus negative 2 times negative 5. Is that equal to negative 3 times negative 5? It sure is. 15 equals 15. So yeah, that's the eigenvector, or one of the eigenvectors, the one I'm going to pick for this eigenvalue. And for lambda 2 equal to negative 2, we do the same sort of work. So let's see, I get negative 3 times x equals negative 2 times x. This is a very different situation. What does x have to be now? There are not multiple answers. There is an answer, though. What's something that you could definitely plug in for x and both sides would be the same? One doesn't work. Negative 1 doesn't work. 0 works. Okay. And the problem is, if you do this for the second equation, you're going to get the same result. You're going to get 5x minus 2y equals minus 2y. The y's cancel, and you get 5x equal to 0. So either way you do this, you're getting x equal to 0. What is y going to be? Anything you want except for 0. You never want 0, 0 is never an eigenvector. So we're going to choose y equal to anything but 0, and the usual choice would be 1. So our eigenvector here is 0, 1. And then our general solution is x of t, y of t equals c1e to the lambda 1 times v1 plus c2e to the lambda 2 t, sorry, I forgot to say t over here, times v2. And I'm going to say a couple things here. One, as t goes to infinity, well, e to the negative infinity goes to 0. E to the negative infinity goes to 0. So both x and y are going to go to 0, which already is speaking to the stability of this system. As t goes on and on and on, x and y get closer and closer and closer to 0. Yeah, this is.
What's the difference between the general solution and the particular?
The particular solution is what you get is when, basically it's when you solve for C1 and C2. So you use your initial conditions, which I didn't choose very carefully, so they're probably terrible to solve for. But to find C1 and C2, you would set, so my initial conditions, if you look back here, I said x of 0 was 2. Sorry, you can't see that, apologies. I said x of 0 is 2 and y of 0 is 10. So I plug in 2 for x, 10 for y, and 0 for t, which is just going to make this 1. So I'm going to get C1 times 1 negative 5 plus C2 times 0 times 0, 1. This one's not too terrible to solve for because having a 0 there makes it so that C1 has to equal 2. And then knowing that C1 equals 2 means that 10 equals 2 times negative 5 plus C2, which gives me that C2 is equal to 20. So my particular solution would be this general solution with those numbers plugged in. Okay, but here's what I really want you to see. Both the eigenvalues are negatives, which means we have a stable equilibrium. So lambda 1 and lambda 2, both negative, means we have a stable equilibrium. And since they're both real, right, they're both real numbers, and we haven't gotten to the imaginary stuff yet, what this actually means is we have a stable node, also called a sink, because everything is going towards it. So both the eigenvalues are negative, you have a stable node. Both the eigenvalues are positive, you have an unstable node. And if you have one of each, which we'll see next time, you have what's called a saddle, where you're kind of going towards it in one direction and away from it in another direction. Kind of like a saddle, right? Like you go down towards it and then you go down away from it. Let me just show you. If we plug this in, sorry, what did I have here? I had dx dt is negative 3 times x, and dy dt is 5 times x minus 2 times y. And you can see that, oh yeah, we are going inwards, right? We're pointing towards the origin, not away from it. So that's a stable node, because everywhere we start, we end up getting pushed towards the origin. Sometimes in a kind of roundabout way, not in a spiral though. This is definitely not a spiral, even though it has kind of a rotation to it. Definitely not a spiral. I'll show you a spiral later, and it'll look very spiral. Like you'll actually go around the origin like many times before you start to actually zone in on it. So spirals look very different. You have multiple circles. I mean, it's a spiral, right? How else can I call it? It's a spiral. All right, I should stop talking because I got to go places.